Okay, so when we ended the last video, we were talking about uniform circular motion, and we said it's caused by a centripetal force, an Fc. Remember, every force is a capital F, and the subscript tells us then where it's coming from. So centripetal force, Fc, is any force that makes an object move in a circle. Any force, okay? It's also the sum of the forces that make an object move in a circle. So if we were swinging something in a circle, a vertical circle, at the top, gravity would be acting towards the center and the tension would be acting towards the center. And so the two of them added together would be the centripetal force. So Fc is a net force. It's like F net. Okay? And it's always, always, always center seeking. It's always acting towards the center. So if we were finding the total force, towards the center would be positive, and away from the center would be negative, right? So down here at the bottom, if we were swinging something in a vertical circle, Fg would be going down and Ft would be going up. And so now to find the centripetal force, Ft's towards the center, it's positive. Fg's away from the center, it's negative, okay? So we need an equation for this centripetal force other than just adding up all the forces. So again, let's go back to thinking about we have some kind of a little ball on the end of a string, and this time we're going to swing it in a horizontal circle, okay? What do you think the force that's required to swing this ball is going to be dependent on? Well, if we were in class, I would be swinging a ball above my head right now, and you would be able to tell that as I sped up, the force needed to change. The higher the speed, the greater the force. And if I took this ball off the end of the string and I put one of you on it and wanted to swing it with the same at the same speed, hopefully you would be able to imagine I'm going to need a lot more force. So the mass of the thing being swung is also going to determine how big the force is. And the final thing is the radius of the circle that it's moving in. The bigger the radius, actually, the smaller the force needs to be. So that's why it's easier on a slippery day to go around a curve that's a really big radius than to go around a tight curve. Okay? And so playing with the stopper, imagining it in your mind, you should be able to see all of these things. The one that the piece that we found experimentally, that it's actually mv squared over r. And this is the equation for centripetal force. Now remember, we're moving in a circle, and it's constant velocity, right? Uniform constant velocity. So the v is like a v-av. And remember, speed is delta d over delta t from grade 10. So as we move in a circle, then once around the circle is 2 pi r. And the time it takes it to go around the circle is the period, or capital T. So this is another equation that we use for centripetal force. And then the third equation that we'll use in this unit comes from the fact that a few minutes ago I said to you Fc is F net. It's a net force. And remember, F net is equal to ma. And so if Fc is F net and m is m, then a must be v squared over r. So the centripetal acceleration is v squared over r. And this is our third equation. Now this one might cause you issues. Okay, sorry, I messed all that one up, so let me rewrite it. mv squared over r. The acceleration one might cause you issues because you might say, but wait, a minute ago you just said it's moving at constant speed. And it is. As remember the diagram we drew yesterday, as it went around the circle, its speed didn't change, just its direction did. And so it created a circle with the speed vectors, the velocity vectors, always being the same length. They were just changing direction. So if the speed isn't changing, how is it accelerating? That goes back to when we first did acceleration in grade 11 physics. And we said acceleration occurs when an object speeds up, slows down, or changes direction. So this object doesn't need to be speeding up or slowing down, because everywhere as it goes around the circle, it changes direction. Okay, and so that's why there's a centripetal acceleration. The little c here tells us it's centripetal. And remember, the word centripetal means center seeking. So in the F net and the A always act in the same direction. They're both always going to point towards the center of the circle. What's going to happen if the force that is acting on it, the centripetal force, is taken away? Well, if we take the centripetal force away, then rather than the object turning, it's just going to go off at a tangent to the circle. It's going to be an object in motion that's going to stay in motion when there's no unbalanced force acting on it anymore. So its velocity vector at any given moment will always go at a tangent to the circle. So if we were in class and I was swinging this over my head, as I would be saying this, I would let it go. And you would see it go off at a tangent to the circle as some of you dove under your desk thinking it was going to hit you. It really wouldn't. And it's only a rubber stopper, so it wouldn't really hurt that much. Okay? So your practice questions tonight, there are 5 of them, and they're really pretty straightforward. They're just using different scenarios of centripetal force and giving you the mass, the velocity, the r, asking you to find FC, or giving you FC, asking you to find r. They're on page 559, numbers 15 to 19. And the only one that's probably going to cause you issues is 17, because it's a vertical circle. And so it asks about when the stopper's at the top and when the stopper's at the bottom. Okay, and so, or whatever it is, I forget what it is, it's going in a circle. But remember, FG at the top is acting towards the center, and FG at the bottom is acting away from the center. In the next video, we will look at specific examples of centripetal force, and then it'll help make 17 make more sense. But before we go there, maybe just a couple of notes on what is centripetal force. Okay, just so that you can refer back to it. So what is centripetal force? Okay, so the first one is any force that makes an object move in a circle. Any force that makes an object move in a circle. In other words, every scenario that what's supplying the centripetal force will be different. Makes an object move in, I'm going to say a circular path maybe, because it doesn't have to be a full circle. The second thing it is a net force. So it's the sum of all the forces acting towards the center or away from the center. And towards the center is always positive. Doesn't matter if it's up or down, but towards center is always positive. Okay? It is not a new force. Okay, so it's not some force you haven't seen. It's just all of the forces that you already know that's this time acting perpendicular to the object. So sometimes gravity is the centripetal force. Sometimes friction is the centripetal force. Sometimes tension is the centripetal force. You know all of them. Okay? The next little thing is if an object wants to move in a circle, it has to have a centripetal force. So if an object wants to follow a circular path, there must be a centripetal force. If not, the object will go tangent to the circle. Okay, we're going to come back to these.